Today I'm going to wrap up our discussion of thermochemistry with a look at another way to calculate the enthalpy change associated with a chemical reaction. And I'm going to start with this example of a reaction between ethene C2H4 gas and hydrogen chloride HCl to form ethyl chloride C2H5Cl. And let's say that we wanted to determine the enthalpy change for this reaction. One way that we could do this is to take the reaction and split it up into reactions whose enthalpy changes we know. And one set of reactions that we can use is reactions for the formation of the reactant and product substances. So, for example, ethene, C2H4, can be formed from its elements, graphite, solid carbon, and hydrogen gas. And the enthalpy change associated with that is negative 84 kilojoules per mole. So I've labeled the enthalpy change here with a little superscript circle indicating standard state conditions, and subscript F labels this as an enthalpy of formation. And in particular, this is the standard enthalpy of formation, which is the enthalpy change for production of 1 mole of a substance from its elements in their standard states. So to form 1 mole of C2H4 from its elements, graphite and hydrogen in their standard states, the enthalpy change is negative 84 kilojoules per mole. And we can write down similar reactions for the formation of hydrogen chloride from its elements, hydrogen and chlorine. And notice that since we are forming 1 mole of the substance, hydrogen chloride, the elements that go into that are going to be half a mole of H2 and half a mole of Cl2. And then finally, we can represent the formation of the product, ethyl chloride, as 2 moles of graphite combining with 2.5 moles of hydrogen gas and half a mole of chlorine gas to form 1 mole of C2H5Cl. And that has a standard enthalpy of formation. And so if we want to combine this set of 3 reactions to calculate the delta H of the reaction that we started with, one thing that we have to pay attention to is that in our original reaction, C2H4 was a reactant, and in the formation reaction down below, C2H4 is a product. So that means that we have to reverse the formation reaction for C2H4, and when we do that, we change the sign for the enthalpy change. So instead of negative 84 kilojoules per mole, this will become positive 84 kilojoules per mole. And then likewise, hydrogen chloride is a reactant in our original reaction, so we need to reverse its formation reaction and switch the sign of its enthalpy change to positive 92 kilojoules per mole. And so now finally we've got all of the reactants from our original reaction are on the left side. The product of our original reaction is on the right side, and we can combine these together. Notice that if you set up these combinations properly, everything that's not a reactant or product of the original reaction should end up canceling out. And so in this case, the graphite cancels out, the hydrogen gas cancels out, and the chlorine gas cancels out. And when we add these together, we're left with our original reaction, C2H4 gas plus hydrogen chloride gas gives us C2H5Cl gas. And the enthalpy change for that original reaction we get by adding together the delta H values for these 3 subreactions. And so that gives us an enthalpy change for our original reaction of positive 39 kilojoules per mole. So if you look at what we've done here, we didn't touch the last formation reaction because that was forming our product, and so in this combination we have the enthalpy of formation of the product, and then we had to reverse the enthalpy. We had to reverse the formation reactions for the reactants, and so we had to turn those enthalpies. We had to change the sign, and so in the combination, those parts were the negative of the standard enthalpy of formation of the reactants. And combining all of this together, we ended up calculating the enthalpy change for the overall reaction by adding up the enthalpy change formation of the products and subtracting the enthalpy of formation of the reactants. And this is a general pattern that we can use for calculating the enthalpy change of any reaction, as long as we can figure out what those standard enthalpies of formation are. So I want to look at another example, and this is a somewhat more complicated reaction. 3 moles of phosphorus pentachloride gas reacting with 2 moles of boric acid to form 3 moles of phosphonyl chloride and boron trioxide and 6 moles of hydrogen chloride. And so we want to find the enthalpy change for this reaction, and we're going to try using the formula that we just discussed. The delta H of reaction is going to be the total enthalpy of formation of the products minus the total enthalpy of formation of the reactants. And so you can look up standard enthalpy of formation for many substances, and for the substances involved in this reaction, these are the standard enthalpies of formation in units of kilojoules per mole. And so we can use these numbers to calculate the delta H for our original reaction. Well, we do need to be careful that we are calculating the total enthalpy of formation of the products and the total enthalpy of formation of the reactants. And so we need to take into account that we have more than 1 mole for many of these substances. And so so we can write down the delta H of reaction in units of kilojoules per mole, and that will be the sum of the enthalpy of formation of the products. So all these guys added together, 3 times the enthalpy of formation of the phosphonyl chloride plus the enthalpy of formation of the boron trioxide, and then plus 6 times the enthalpy of formation of hydrogen chloride. And then we subtract the total enthalpy of formation of the reactants, which is 3 times the enthalpy of formation of the phosphorus pentachloride and 2 times the enthalpy of formation of the boric acid. And so now finally we've got all of our all these numbers are ready to go, and we can type them into our calculator. You do need to be very careful with the negative signs. It's really easy to lose track of minus signs or to subtract things when you mean to add them, and vice versa. So you need to be careful, but assuming we do this arithmetic correctly, we end up with final result of negative 305.282. And then for our final answer, we do want to round this off. The precision of our answer is going to be limited because we've got several of the delta H of formation values that we used were uncertain in their first decimal place, and so that limits the precision of our answer. We should round that off to 1 decimal place, and then putting the units back in, we get that the delta H of the original reaction is negative 305.3 kilojoules per mole. So this idea of combining the formation enthalpies of the reactants and products to calculate an enthalpy change for a reaction is it's a very useful idea, and it's a standard thing to do. And so in order to be able to make use of this pattern, the enthalpies of formation for many substances have been tabulated. They've been measured to high precision. And so you can look up in many textbooks, also online, you can look up the standard enthalpy of formation for many hundreds of substances. And now, when you look up these tables of standard values, there are usually several other thermodynamic properties that are listed along with the standard enthalpy of formation. I'm going to ignore those for the time being. They'll be the subject of a future video. But one thing that you'll notice from these tables of enthalpies of formation is that the standard enthalpy of formation of an element is always 0. And that should make sense because the standard enthalpy of formation is the enthalpy change for the formation of 1 mole of a substance from its elements in their standard states. And so if you're forming an element from that element, well, there's nothing happening there, and so the enthalpy change for that is 0. Another thing that you'll probably notice when you look at these tables of enthalpies of formation is that many of those delta H values are negative. And that reflects the fact that for most compounds, they have an enthalpy that is below the enthalpy of the elements. In other words, compounds tend to have less energy than their constituent elements. And that's one of the reasons why so few elements are found in nature. Most elements end up combining to form compounds because compounds, generally speaking, are lower in energy. They have a lower enthalpy. And so I want to look at another chemical reaction here. I want to look at the reaction between zinc metal and hydrochloric acid to form hydrogen gas. So here's a photograph of a piece of zinc wire that's been dumped into a test tube full of hydrochloric acid, and you can see little bubbles of hydrogen gas forming. So the balanced chemical equation for this process is solid zinc reacting with 2 moles of hydrochloric acid in aqueous solution to form a solution of zinc chloride, ZnCl2, and hydrogen gas. Now, if you were to look up the standard enthalpies of formation of all the substances in this reaction, you might find that you can't find all of them in many thermodynamic tables, and specifically the hydrochloric acid and the zinc chloride, the delta H of formation for those substances is not found in many thermodynamic tables. And the reason why it's not listed has to do with the fact that those are aqueous ionic substances, and so when they are in water, those ions are actually dissociated. And so something like HCl in water, it dissociates into ions, and so this really represents 2 moles of hydrogen ions in solution plus 2 moles of chloride ions in solution. Likewise, aqueous zinc chloride really represents the zinc 2 plus ion in solution and 2 moles of chloride ion in solution. And so the enthalpy of formation for those ions can be found. But before we look those up, we can make things a little bit easier for ourselves if we notice that the chloride ions are not actually participating in the chemical reaction here. They're starting out in aqueous solution and they're ending up in aqueous solution. So those chlorides are spectator ions, and we can cancel them out and just look at the net ionic equation for this chemical reaction, and that is solid zinc reacting with 2 moles of hydrogen ions in solution forms 1 mole of zinc 2 plus ions in solution plus a mole of hydrogen gas. And if you look up the enthalpies of formation for these substances, solid zinc is an element, and it's in its standard state. Zinc is a solid at room temperature, and so its enthalpy of formation is 0. If you look up the enthalpy of formation of the hydrogen ion in solution, that's also 0. Now, H plus is not an element, but its enthalpy of formation is taken to be 0, and that's something that we can discuss at another time. But for now, the number that we would find in a table is that the enthalpy of H plus in solution is 0, and then the enthalpy of formation for the zinc 2 plus ion is negative 153.9 in units of kilojoule per mole. And then hydrogen gas is, again, an element. It has a standard enthalpy of formation of 0. And so now we can take these numbers, put them into our formula, and find that the standard enthalpy of reaction for this process is negative 153.9 kilojoules per mole. Okay, now before I leave you today, I just want to say a few words about what's actually going on here when we use this formula, that the standard enthalpy of reaction is equal to the total standard enthalpy of formation of the products minus the total standard enthalpy of formation for the reactants. What we're really saying here is we want to find the standard enthalpy change for a reaction between some set of reactants and some set of products. The enthalpy change of formation corresponds to the process where we're forming the reactants and products from their elements. And the thing is, remember that the set of atoms in the reactants and the products is the same. Those atoms are just being rearranged. And so the set of elements that are forming the reactants and products is also the same. So this is really the same set of elements. And so in going from the reactants to the products, that's equivalent to going from the reactants to the elements and then back down to the products. And so what we're saying when we use this formula is basically that the reaction, the process of going from reactants to products, is equivalent to starting at the reactants, decomposing them into their elements, and then forming those elements into the products. And so the overall change in either case is the same. We're still going from the same set of reactants to the same set of products, and the enthalpy change is going to be the same either way. And so that's why we can use this formula.